Hey there, can folks hear me okay? Wonderful, thank you. Okay, so today I am going to, actually let me share a screen here, hang on. Go to this, get rid of that. Here we go. Okay, so first let's go over the upcoming deadlines. These are the deadlines for the rest of the semester. We have this Friday, homeworks 11 and 12 are due. They are shorter than typical homeworks, so having 2 of them due this week shouldn't be too bad. Small group activity number 5 is now available, and it will be due a week from today, so next Thursday. The small group activity number 5 quiz is opened at, once the activity itself is the due date for that it comes in. And my hope is to release midterm exam number 4 on that same time, 5 o'clock on Thursday of next week. Now, I've announced this before, but in case anybody hasn't seen it, I realized that it doesn't make a lot of sense to have midterm exam 4 and then a portion of the final exam covering the same material in the same time period. Testing you twice over the same thing in the same time period just doesn't make a lot of sense. So what I'm going to do is have the midterm exam 4 count as midterm exam number 4. We're then going to, in addition, cut that grade in half since the final exam portions are out of 50 points, and that becomes the 4th portion of your exam grade without having to take anything extra. The Friday immediately following that is when homeworks 13 and 14 are due, covering electrochemistry and redox reactions, and that is when the small group activity number 5 quiz is due. The following Monday is the beginning of exam week, a final exam week, and the 3 parts of the final exam will be released at that point. Each part can be taken separately. Each part is out of 50 points. Each part will have a time limit of 1 hour, and each part can apply redemption points to your midterm exam grade. The way this works is that whatever your final exam grade portion for that part is, double it, and if that doubled value is larger than your midterm grade for that part, then your midterm grade will be increased to that doubled score. It does not work the other way around. It does, if your doubled exam score is lower, it does not lower your midterm grade. It also does not work the other way around, where your midterm grade does not in any way affect your final exam grade. The grade projection spreadsheet that I distributed does this for you if you want to try running some scenarios with it. Midterm exam number 4 and all parts of the final exam are due on the Friday of exam week at 5 p.m. Okay. I have posted a bunch of old content videos from about 7 years ago when I was teaching a general chemistry course back at Oklahoma State University. The reason that I didn't post these earlier for you guys is because, for several reasons. One is that the videos very heavily reference the textbook that we were using at the time, and that is not the same textbook that we are using here at BSU. In addition, the audio quality is kind of hit and miss on these, and so you may have to really crank up the volume in a few cases to be able to hear what's going on in them. Nevertheless, they can be useful because they are presenting much of the same information that we're talking about in this class here from my perspective, so that you can see how I approach these various components. The classes on Monday and Tuesday of this week used some of the PowerPoint presentations that I had developed for those content videos when I was going through my review of Hess's law and standard heats of reaction. So that material is probably presented in those videos in a little bit more of a coherent fashion than it was in the Monday and Tuesday lectures. So I have a sequence that is on thermodynamics. That is a lot of the background information that you need before getting to the whole entropy and spontaneity kind of thing. There are a few that are on sort of general review stuff that might apply to the stuff for the final exam: aqueous solutions, precipitation reactions, and acids and bases. And then there is a sequence on redox reactions, and that is going to be the topic for next week. These are not assigned videos. You don't have to go in and do them, and there are no embedded quizzes associated with them. But they do present a lot of the same information that we're going to be going over in the redox reaction and electrochemistry material for next week, if you want to be looking at it. The first two in that sequence on effective nuclear charge, that one is mostly useful for determining, if you need a review of how to determine core charge, which is what is used to determine both formal charges and oxidation numbers. And then Lewis structures goes through the way to calculate formal charges, which is the basis for calculating oxidation numbers that we're going to use in the video on redox reactions and so on. So the last three are specifically, last three videos are specifically related to the material that we're going to be covering next week. The first two in that sequence are background material if you don't feel as though you have a good understanding of core charge and how to use core charge in calculating things like formal charge. Okay. The plan for today is that there is one topic that I didn't get to on the Monday and Tuesday lectures. I will go through that topic first, and then I will go through some muddiest points, and then open up the class to questions about any of the material that you have questions on. Does anybody have any logistical questions before I start getting into the content? Okay, let's go into some content. So where we're going to start here is looking once more at the Appendix G from your textbook, which has a table of standard thermodynamic properties for a variety of substances. We talked about this a bit on excuse me, Monday and Tuesday. Where we have the standard enthalpies of formation, the standard Gibbs free energies of formation, and the absolute entropies at under these standard conditions. But one thing we didn't really talk about very much is what this little degree sign that you're seeing up here means. And it's a little bit important to understand what that means, because there are times when we need to use versions of these values that do not have that little degree sign. What the degree sign means is standard conditions, and that corresponds to three things: a temperature of 298.15 degrees Kelvin, or 25 degrees C. If you have a gas, you're looking at the pressure of that gas being 1 bar, and a bar is roughly the same as an atmosphere. And if you have a solute, then you're looking at a concentration of 1 molar. So the values that are tabulated in here are for those conditions. And so the only gas that I have listed here in the little excerpt from the table that I have listed is aluminum vapor. And so these values that you see listed here are for a full 1 bar of pressure of aluminum gas, which is kind of an odd thing to imagine, because at the temperature 298.15 Kelvin, 25 degrees C, the vapor pressure of aluminum is nowhere near a bar. So these are values that are for a substance under conditions where it actually cannot exist. So it's a very odd kind of thing. Now, these values are accurate because it is a theoretical construct that we have aluminum vapor at 1 bar, and we can determine what its delta H of formation, delta G of formation, and its absolute entropy would be under those conditions very precisely. I mean, we even see 5 significant digits here for the absolute entropy. But if we are trying to apply this to a to a real system, we would have to move our conditions away from those quote unquote standard conditions. So we have a similar case here with the aluminum 3+ concentration. So because that is a solute, the concentration of it would have to be 1 molar in that substance in order to have these particular values. So the question then becomes, how do we do this modification to other conditions? And this equation right here is the way that we do that. So we see the delta G standard with the degree sign over on the right-hand side, which corresponds to what we would get for the reaction if we used Hess's law and these various standard values to determine the delta G for the reaction. But then we modify the delta G standard by using this plus RT natural log of Q term. Here we have R is the gas constant, we have T is the temperature measured in Kelvin, and we have Q, the reaction quotient, which you remember has the same form as the equilibrium constant, either in terms of pressure, partial pressures, or in terms of concentrations and molarity. But what this means is that when we put the actual conditions we have into Q, then we are able to adjust our delta G away from the conditions where everything is at 1 molar or everything is at 1 bar, to find the conditions, the delta G under the conditions that we're actually dealing with. Now, this expression ends up having a much more important consequence that we can use when we recognize that there are two things that are true at equilibrium. At equilibrium, delta G equals 0. So we talked about that a bit on both Monday and Tuesday. The idea is that a process is spontaneous if its delta G is less than or equal to 0. And remember that if delta G is greater than 0, then it's non-spontaneous, but the reverse reaction is spontaneous. So if we have delta G equals 0, then that means the reaction is spontaneous in both directions, which is another way of saying it's at equilibrium. So delta G equals 0 is true at equilibrium, but at equilibrium also Q, our reaction quotient, is equal to K, the equilibrium constant. If we plug those two values into the expression that I put up above, delta G equals delta G standard plus RT ln Q, we get this expression, 0 equals delta G standard plus RT ln K. All I've done is plug in those two equalities that are specific to the equilibrium condition into the expression below. We can solve this for delta G standard, and we find that if we know R, we know the temperature, and if we know the equilibrium constant, then that gives us the delta G standard for the reaction. But this is probably more useful if we instead solve it for K, which is what this bottom expression is down here, because we can use tabulated values for delta H of formation and the tabulated values for the absolute entropies to find the delta G standard for any reaction at any temperature that's close to 298 K, because we're accounting for the temperature dependence in both the definition of delta G as delta G equals delta H minus T delta S, and accounting for it here in this exponential expression. So at whatever temperature we're operating at, we can calculate our delta G from the tables. We have R and T, and we can find the equilibrium constant. So the point of this is that for any reaction that you can write down, where you have entries in a table for enthalpies of formation and absolute entropies, which frankly we know for most substances, we can calculate through this expression what the equilibrium constant for that hypothetical reaction is without even performing the experiment. There are experiments you can write down that have never been done before, and we can find out what the equilibrium constant for that reaction is by using these tabulated values. Okay, that's it on the new material. Does anybody have any questions on this kind of this type of content? How to use this expression to find a delta G at a different under different conditions, and the implications of that in terms of the relationship between an equilibrium constant and the delta G of reaction. All right, I'm not hearing any questions, seeing any questions. So what we will do now is move on to some muddiest points things. I did not actually successfully make a PowerPoint presentation for this that has all of that information in it. So I'm going to be looking at a few of them off of Piazza as we go. So there was one question which said there are understanding that elements in standard state, which is how we define the reactants in a formation reaction, and was asking the question, is there ever a case where an element is not included? And if there is, would this be necessary to know? And the answer to that is no, there is not. You can always do that. So I'm going to show an example of this. Actually, let me bring this over here. And I'm going to expand that a bit. And I'm going to bring this over here. And what we're going to look at is an example of writing down a formation reaction for an arbitrary compound. So taking a compound from this table, and let's pick one that is a particularly complicated one so that we can work with it. So I'm going to look here at this aluminum trichloride with 6 waters of hydration as a solid. So let's write this out here. Leaving out the dot because I don't remember how to do that in this particular program that I'm using. And so if we want to know what the formation reaction is for this compound, excuse me, I left out the 6, didn't I? 6, H2O. So what we do is we put our reaction arrow and we are saying we're going to make this. All right, so we're going to make 1 mole of it. We now need to, there shouldn't be a 2 there, should there? I don't know what I'm doing. Okay, get rid of that. I now think I have it correct. All right, what you do is you simply go through and look at each of the elements. So we have some aluminum, we have some chlorine, we have some hydrogen, and we have some oxygen. Now we should go back and identify what is the standard state under at 1 atmosphere pressure or 1 bar pressure and 25 degrees C of each of these compounds. So, or each of these elements. Aluminum, in it, we know is a solid. Chlorine is a diatomic gas at room temperature. Hydrogen is a diatomic gas at room temperature, and oxygen is a diatomic gas at room temperature. Now we balance the stoichiometry. How many aluminums do we have on the right-hand side? 1. How many chlorines do we have on the right-hand side? 3, so we need 3 on the left, which means we need to take 3 halves of a Cl2. How many hydrogens on the right-hand side? 12 atoms, which means we need 6 diatomic hydrogen molecules. How many oxygens are on the right-hand side? 6, so we need 3 diatomic oxygen molecules. So this is the formation reaction for AlCl3.6H2O. Any compound you write down, you can do this with. You simply take whatever the elements are that are part of the compound on the right-hand side, you put them on the left-hand side, you figure out their standard states, and you balance the equation in terms of the number of atoms on both sides. you have to have 1 mole of the product on the right-hand side, which means that you may have to use fractional coefficients on the left-hand side if you're dealing with something in a standard state that has multiple atoms in it. That's it. That's the procedure. Does anybody have any questions on that? Okay. All right, let's see now what else we have for muddiest points. Okay, some questions on entropy. When comparing molecules to each other, would a molecule with more entropy have a higher change of entropy value overall? Okay, so I think what's going on here is that there's some confusion about what we mean when we talk about a delta S. So whenever we are looking at any reaction, reactants going to products, for a delta anything for that process, what we mean is, delta X for whatever X is, we are meaning the X of the products minus the X of the reactants. So, if we are talking about entropy, delta S of the process, then we are meaning the entropy of the products minus the entropy of the reactants. This is similar to what I went over in terms of altitude as being a state function. And so for a change in altitude, what we look at is the final altitude minus the initial altitude. So if we climb up by a mile, then our delta altitude is 1 mile, the final altitude minus the initial altitude. Now, it is important to remember that this does not mean that, so if we apply this, for example, to enthalpy, this does mean the enthalpy of the products minus the enthalpy of the reactants. The problem is we don't have any clue what the enthalpy of the products is or what the enthalpy of the reactants is. What we have instead is the enthalpies of formation of the reactants and the products. These are not the actual enthalpies of the products or the enthalpies of the reactants. These are the changes in enthalpy of the formation reaction. So while it is true to write that the delta H of the reaction is the enthalpy of the products minus the enthalpy of the reactants, we cannot actually calculate it this way. We have to do it instead by using the sort of box notation idea that I introduced before for Hess's law, so that we can tell, do we want the enthalpies of formation of the products minus the enthalpies of formation of the reactants, or do we want, if we're using something other than formation, the enthalpies of combustion of the reactants minus the enthalpies of combustion of the products, something like that. So, so going back to the question that spawned this, when comparing molecules to each other, would a molecule with more entropy have a higher change of entropy value overall? I'm a little bit confused about what that is asking, because what we need to do is look at the entropy of the products for whatever reaction we're studying versus the entropy of the reactants. So for example, if we've got something A that's a liquid plus something B that's a liquid, which goes to something C that's a gas, plus something D that's a gas, then we have here liquids going to gas, and gases have higher entropy, so the delta S is going to be positive. We also have 2 things going to 3 things. And so having more separate molecules means that you have a greater possible number of ways to arrange those molecules. And so for 2 reasons, this reaction would have a positive delta S. So that's how you go about thinking about these about entropies of individual molecules, and then how they end up affecting the entropy of a process, which is what we're trying to really look at here. Okay, does anybody have any clarifying questions about that kind of idea of how to think about entropy in a reaction when we are trying to compare reactants and products? Okay, so there was a question about terminology, the difference between a change of entropy versus a standard entropy change. So a change of entropy is, given a reaction, what is its delta S? A standard entropy change would be a delta S for some kind of standard reaction. So you could imagine a standard reaction being a standard formation reaction, and you would have a delta S of formation for it. But because we actually are able, unlike enthalpy, for entropy, we actually are able to determine the absolute entropies. Standard entropy entropies of reaction are typically not tabulated. So you notice we have a standard enthalpy of formation, a standard Gibbs free energy of formation, but we have an absolute entropy rather than a standard entropy of formation that's being tabulated here. So I cannot think of a context in which you would actually be using this idea of a standard entropy change. So in terms of a delta S, it is the change in entropy for whatever reaction you are studying. All right, there is apparently a Newton question which said the entropy of water at 0 degrees C and 1 bar would be what? And it had some choices. So the choices were equal to 0, a negative value, the absolute entropy of water under those conditions, and the standard entropy of water. Okay, so let us look at these one at a time. Equal to 0. What are the conditions under which an entropy is equal to 0, an absolute entropy? Somebody could try to type that answer into the chat. That would be wonderful. So this is the third law of thermodynamics. And nobody's brave enough to take a guess. So for S to be 0, what would W be? Because what do you take the natural logarithm of and get 0? One, correct. So we need to have a substance, a form of a substance that has only one possible way of being arranged. And so what that means is it needs to be a perfect crystal, and it needs to have no energy, so that there's no energy distributed amongst the various molecules. So that means at 0 degrees Kelvin. Well, 0 degrees C is not 0 degrees Kelvin. So this one cannot be correct. A negative value. Is it possible to take the natural log of some value W and get a negative value? What would we have? What would W have to be for us to get a negative value taking the natural logarithm of it? To figure that out, 0. Okay, so let's less than 1. There we go. That's a great answer to it. So let me show you what a log of x looks like plotted from 0 to, say, 2. Oh, I need to say x, comma. Don't worry about how this works. So in order to get a negative, a log of W to be negative, we would have to have W be between 0 and 1, less than 1. But W, remember, is counting up the number of ways of arranging the system. That can never be lower than 1. And it doesn't come in fractions, it comes in whole numbers. So we can never have a negative entropy. Okay. Down here, the standard entropy of water, I said in the previous question that we don't really talk about standard entropies of water. This isn't really a thing, it doesn't really happen. So by process of elimination, we hope that this one is going to be right, and it is indeed right. The absolute entropy of water under those conditions. So because we are able to calculate absolute entropies, we have this reference point of a perfect crystal at 0 degrees, and we figure out how much more entropy you have above that level. We can calculate an absolute entropy for anything at any temperature. And so that is indeed what is meant by the entropy of water at 0 degrees and 1 bar. Okay, the next set of questions I see on Piazza are asking about determining spontaneity given given a delta H and a delta S. So, whoops. So what you always need to remember in this case is 2 sets of facts. Delta G equals delta H minus T delta S, and delta G greater than 0 means non-spontaneous, which also means that the reverse reaction is spontaneous. Delta G less than 0, which means spontaneous, and just for completeness, non-spontaneous, and delta G equals 0, which means both forward and reverse reactions are spontaneous, which also means equilibrium. So if we combine these ideas, then we can take any given values of delta H and delta S and figure out when is delta G going to be less than or equal to 0. So if we remember, if we have a delta H that is negative and a delta S that is positive, then this term is negative and this term is negative. And so there is no way for delta G to ever be 0 or positive, which means that the reaction will always be spontaneous because delta G will always be negative. If delta H is positive, And if delta S is negative, then this term and this term will both be positive always. And so the reaction can never be spontaneous, and the reverse reaction will be spontaneous. If one of them, if delta H is positive, delta S is positive, then this reaction is positive, meaning at low temperature where this is negligible, it's non-spontaneous. When temperature gets big, then this term will get bigger than this one in magnitude, and the overall reaction will become, the overall delta G will become negative, and we end up with a spontaneous reaction at high temperatures. And the reverse would mean that it's spontaneous at low temperatures and not at high temperatures. All of that you can figure out by remembering these 4 fundamental facts. Okay. All right. I'm going to now dive back into Piazza and see what else I can find that people are confused about. That's a duplicate. That's a duplicate. Which other? Okay, that's a duplicate. Some questions about next week's material. Okay, there's a question here. For a combustion reaction, I thought it would negative enthalpy and positive enthalpy. So for combustion, I thought it would always be a positive entropy change because particles are dispersing. But according to Newton, it can be negative as well. How? Okay, so let's think about this. So a combustion reaction is taking some compound A, reacting it with oxygen to form combustion products. So if A has carbon in it, then the carbon turns into carbon dioxide. If A has hydrogen in it, it turns into water. And so is there a way for the entropy change for the reaction to become negative? Let's see. So if we have, let's say, H2, and we are burning that, then we are making H2O. And so we would need to have 2 of those and 2 of those for our combustion reaction. Or we could write this as this with 1/2 here. Either way works. And in this case, we have 1 molecule of gas, and a 1/2 molecule of gas, or let's think about it in moles. So we have 1.5 moles of gas on the reactant side and 1 mole of gas on the product side. So we're actually going to fewer numbers of moles of gas. And as a result, we would expect that the entropy in this case would go down. So, and that's because we have fewer molecules on the right than we do on the left. So there's nothing special about combustion that says entropy has to go up. Now, most of the things you burn will produce more molecules of combustion products than you started with. It's just that there are a handful of examples of the opposite being the case, where the reaction occurs tying up the oxygen into fewer molecules than you started with during the combustion process. So that's what's going on in that case. All right, so we have, it's looking like I may have covered most of the muddiest points. So what I'm going to do now is I'm going to open up, I'm going to change the security settings so people can unmute themselves if you'd rather ask questions verbally rather than sending them through the chat. So clarifications on anything we've gone over already, or if you have other questions of your own that you'd like us to go over, whatever. What can we talk about? Okay, in the chat, calculating free energy change. Okay, let us do an example of calculating free energy change. And so what I'm going to do here is I'm going to show you a way that you can practice sort of the sequence of questions that are just sort of a natural sequence to have for any of these sort of thermochemistry questions. So I'm going to come over here, put this on one side. I'm going to open up a Google tab, and there are two things I want to open up here. One of them is going to go to our textbook, and in one tab I'm going to open up our Appendix G, which has the standard thermodynamic properties for selected substances. And you see this is a very extensive kind of list that we have. There are a lot of things in here. And I'm going to move to the carbon section. So here we have carbon, and I'm going to pick something off of here, and I'm going to just write down a reaction for it. And so because we frequently care about the thermodynamics of burning things, I'm going to do a combustion reaction. But what you could do is look through the textbook or do a Google search and come up with any chemical reaction you want, and you can follow the same process that I'm going to be doing right now. So I'm going to pick as our compound, I'm going to pick ethanol or methanol here. So CH3OH liquid. So CH3OH liquid. Methanol is the primary substance that is used in windshield washer fluid. So if we are combusting this, we are reacting it with oxygen, and we are forming combustion products. So CO2 gas and H2O gas. Now we need to balance our equation. We only have one carbon on the left, so we have one carbon on the right. We have 4 hydrogens on the left, so we need 4 hydrogens on the right, so we need 2 waters. That means that we now need 2, 3, 4 oxygen atoms, so this needs to react with 2 oxygen molecules. So this is the reaction we are going to try to calculate some free energy changes for. So remember that delta G equals delta H minus T delta S. So what we need to find are the delta H for this reaction and the delta S for this reaction. So let's do delta H first. And actually, I'm going to do them both so that we can read off of the chart at the same time. H delta S equals. And so if we don't remember, we imagine that the things that are tabulated here are enthalpies of formation, which means that our little diagram is going to be, I can't really do that in here very well. So what I'm going to do is add another thing we have here. So I'm going to put a text box here that says reactants. I'm going to make this be our box notation that I introduced before. We'll do this, reactants. Products. And since we're dealing with formation reactions that we are using to as tabulated values, our convenient intermediates are elements in standard state. I'm going to draw in our arrows. We have that. Formation reactions start from elements in standard state and go to the compounds. They start from elements in standard state and they go to the compounds. And so our scenic route that we take going from reactants to products through the elements in standard state go against the arrow for the reactants and with the arrow for the products. So that reminds us that what we need to do is to take the delta H's of formation of the products minus the delta H's of formation of the reactants. Now, let me fend off a point of common confusion here, because remember I did something similar for the case where we were using enthalpies of combustion instead of enthalpies of formation. And in that case, we had the arrows going the other direction because a combustion reaction goes from the compound in question to combustion products. And the point of confusion here is that what we are studying right here is a combustion reaction. Whereas, and so that puts people in the mindset of, oh, we need to use the combustion in the combustion formulation of this. But that's not what we're doing. What we're doing is we are using heats of formation in order to figure out the delta H for a combustion reaction. So the question is, what are the reactions that we have known delta H's for? And in this case, they are formation reactions, and so we've used this formulation here. Okay, with that in mind, we want to do delta H's of formation of the products minus the delta H's of formation of the reactants. So our first product is carbon dioxide, and let's notice that our first column is the heats of formation, and the last column is the entropies, the molar entropies. So let's go down and find carbon dioxide gas. So we have delta H is going to be minus 393.51 kilojoules per mole. We have entropy for that same thing is 213.8 joules per mole Kelvin. Okay, so we've done this one. We now need to do the water. So we go down to the hydrogen in here. So H2O gas. So this is going to be minus 241.82 kilojoules per mole, but we have 2 moles of it, and so we need to put a 2 in front. Same thing here. Our entropy, our absolute entropy for water gas is 188.8 joules per mole Kelvin. Okay. So we've now done our products. We now move over to our reactants. So let's find methanol. So we go back up to carbon. We find CH3OH right here, and we're looking at the liquid version of it. So we have minus, because we are subtracting the reactant heats of formation, minus a negative 239.2 kilojoules per mole. Down here, we are subtracting the reactants, subtracting methanol 126.8 joules per mole Kelvin. Now we move on to the oxygen. Now, without even going down and looking, you should be able to identify what the enthalpy of formation of O2 gas is. Can anybody tell me that number? Zero, says Lael. That's exactly right. How do we know that? Well, let's imagine writing the formation reaction for O2 gas. It's O2 gas goes to O2 gas, which is no reaction. So there's the enthalpy of that change is zero because there is no change. This is one reason why it is very useful to remember what a formation reaction is. If you're already an element in standard state, its enthalpy of formation is zero. So the top one here is done. The bottom one, however, because we're not dealing with entropies of formation, we're dealing with absolute entropies, we actually do need to look up that value. So we go find oxygen. Oxygen? Here we go, O2. And we find the absolute entropy for oxygen is 205.2 joules per mole Kelvin. And we are subtracting because it's a reactant, and we need to multiply it by 2 because we have 2 moles of it. So our delta H is going to be negative 393.51 minus 2 times 241.82 minus a negative, so plus 239.2. And so we get a delta H for the reaction of minus 637.95 kilojoules per mole. For our delta S, 213.8 minus 2 times 188.8 minus 126.8 minus 2 times 205.2. We find that we have minus 701.0 joules per mole Kelvin, for, excuse me, equals that right there. Now, did I do all of that right? Why was this one negative? That one should not be negative, should it? That should be positive. That makes a lot more sense. Okay. 54.2. Let me double check that. We want to make sure that the H2O gas entropy is in fact a positive number. I passed it, didn't I? H2O gas is a positive number, 188.8. So that's correct. All right, we now have our values for delta H and for delta S. So now we're going to use this expression right here. So our delta G is going to equal minus 637.95 kilojoules per mole. We are going to then multiply, we're then going to say minus T times our 54.2 joules per mole Kelvin. And so whatever temperature we want to study this at, we then plug that in and determine our delta G. So if we're doing it at room temperature, then we would plug 298.15 in for this. We need to remember to convert from joules to kilojoules so that we can add these things together. So we need 1 kilojoule over 1,000 joules. And so minus 637.95 minus 298.15 times 54.2 divided by 1,000. And we find that we have a delta G of reaction equals minus 654.11 kilojoules per mole. We can then, if we want to, determine what our equilibrium constant for this reaction is. Remember what we covered at the beginning of this class. K equals E to the minus delta G over RT. So we take our delta G minus 654.11 kilojoules per mole. We then divide that by our value of R. So I'm going to look up our gas constant. Okay, so we have joules per Kelvin mole, so that's a good one to start with here. So we'll do 8.3146. We probably don't need more digits than that. Joules per Kelvin mole. Now we need joules and kilojoules to cancel, so we're going to have to do 1,000 joules, 1 kilojoule. We also need our temperature here in the denominator, so we need 298.15 Kelvin. All our units cancel. And so what we are going to do, so I'm going to move this. I have a yowling cat in the background. I apologize for that. So that comes from the negative here. The whole thing has a negative here. I'm going to copy this. Actually, I'm going to cut it. I'm going to say E to that thing. We calculate that and we find our equilibrium constant. So minus a negative, so 654.11 divided by 8.3146 times 298.15 divided by 1,000. Okay. And then we take E to the 263.861, and we find that our equilibrium constant is a staggering 3.9 times 10 to the 114. So this is one of those cases where you would look at this and say, yeah, that's not really an equilibrium, that's a one-way reaction. You're not going to have any reactant left at all. So that is the sort of sequence of steps you would go through to go all the way from a reaction that you're given and then determine what the delta H is, the delta S is, the delta G is. You determine it's spontaneous because delta G is negative, and then you can find the equilibrium constant and do things with the equilibrium constant at that point. So that is the sort of connection of all of these kinds of ideas. Anybody have any clarifying questions on this sort of pathway? And while anybody's formulating such questions, I'll point out that this is a really easy thing for you to practice. Look up any reaction you want to, and then go through calculate its delta H, calculate its delta S, calculate its delta G, see under what conditions it's spontaneous. In this case, we have both delta H is negative, delta S is positive, so this reaction is always spontaneous. And then go through and do this. For any reaction, you can find that you can find your equilibrium constant this way. Okay. If there are no questions on this, are there any other topics you would like me to talk about? We have about 15 minutes left. Nobody has any questions? Okay, if nobody has questions, I'm happy to let everybody go early. Feel free to use my office hours. I am planning to have quite a number of extended office hours during finals week while the exams are going on. I know that I will have quite a lot of them on Wednesday, Thursday, and Friday of that week. I may be able to have some on Mondays and Tuesdays as well. I may even be able to have some on the Saturday before, when both the Friday and the Saturday before, when midterm exam 4 is out, but obviously not due till the end of the following week. If any of you want to try to get midterm exam 4 out of the way, I'll be available for talking about that then. Thank you all. And next week is going to be same general idea. Monday and Tuesday, I will be doing the bulk of the introduction of the material for redox reactions and electrochemistry. And if there is more material than I can cover on Monday and Tuesday, I will do it on Wednesday and Thursday. But the bulk of Wednesday and Thursday will be Q&A, muddiest points, and so on. Thank you very much.
Hey, Kevin.
Yes, sir.
I did and I just found what I was doing in some of the homework, and I had a question on your calculations for the free energy change.
Okay.
So in the homework, it was saying that you actually have to add the products together and then subtract the addition of the reactants together. Do you still have your thing pulled up?
Yes. So, yeah. So, right. And so mathematically, it's the same thing. So if you have product 1 and product 2 minus reactant 1 minus reactant 2, that's the same thing as product 1 plus product 2 minus reactant 1 plus reactant 2.
Okay, well, I was just kind of curious because on your delta H, you did the negative 393.1 or 51 minus 2 times that. So I thought,
right. Okay. So what's going on there is that the value was negative.
Oh, okay. I guess I didn't see that.
Right. And so what I did was I first wrote it as minus that value, and then I added the times 2 later. And so the 2 ended up separating the minus sign I had from the number. So I agree that that looks a little confusing the way I did it, but the rationale was I entered it as a minus sign, and then put in the 2 times.
Okay, that makes more sense. It was just looking at it, I was just kind of cute.
Absolutely. Thank you for asking that and getting it clarified.
All right, that's all I had. Thanks.
All right, you bet.
I just wanted to let you know that I am trying to get like a practice worksheet together for
Cool.
everyone for at least like the exam 4. So
sure, absolutely. So what I'd recommend for that is pick some example reactions like the one I just did here, and then go through how do you find the delta H, delta S, delta G, K. And then maybe some conceptual questions about under what conditions is it spontaneous, under what conditions is it not, meaning what temperature. In what way, if you look at the reaction and say, should the delta S be positive or negative, does that make sense? Things like that.
Cool. I know my professor always had us analyze like the graphs to kind of like figure out when things, and it kind of just helps you conceptualize when like delta S and like delta H, like whenever their signs change, what happens.
Right.
So I was
and
gonna
th-
try to
and
throw
there's a
those
nice
on there.
figure for that in the textbook that shows the 4 different cases for, positive delta H, negative delta H, positive delta S, negative delta S.
Cool. Yeah. So I'm gonna throw those in there and be like, explain these to me.
Fantastic.
So just wanted to let you know. So
Absolutely. Thank you so much for all you do. Really appreciate
yeah, no
it.
problem. Have a good one.
You too. Bye-bye.